right. Hi, everyone. So this lesson is going to be about gas stoichiometry. And I'm actually just going to jump into some examples here because you've already learned about stoichiometry. You've already learned about the ideal gas law. And really what we're doing here is we're just using another application of stoichiometry. So it just will make more sense if we just do some examples. So our first example here, we have this chemical reaction, and then it says what volume of oxygen will be produced from 10.5 grams of potassium chlorate at 1 atmosphere and 25 degrees Celsius. So our givens here, we have 10.5 grams, so a mass of the reactant. And then we have a pressure of 1 atmosphere, and our temperature is 25 degrees Celsius. But of course, we do not want Celsius. We want Kelvin. So I'm going to add 273 to that, and I get 298 Kelvin. Now our R, our universal gas constant, we know is 0.0821 as well. And then I want to know the volume of oxygen. Now you should be kind of recognizing some of these variables over here on the left-hand side where I have a pressure, I have a temperature, I have a universal gas constant, I want a volume. So you should kind of recognize that, oh, I need to use the ideal gas law in order to find the volume of oxygen. However, we do not have N, right? Our number of moles. So this is where stoichiometry comes in. So in order to solve for volume of oxygen, I'm going to need that number of moles of oxygen gas in order to plug this into this equation and solve for volume. So what we need to do here is I need to first find the number of moles of oxygen, which is again our N, using stoichiometry, because I am given a mass of the reactant, and from that mass, from stoichiometry, I can find how much oxygen is produced. All right, so that's our first step. So I know that I have 10.5 grams of potassium chlorate, right? It's this right here. Now, in order to get from one thing to another in a chemical reaction, remember first I have to convert to moles. And how do we do that? Yes, that's true. We're going to divide by the molar mass of potassium chlorate. So we first have to look at the periodic table, and then we're going to add up the molar masses of potassium, chlorine, and then 3 oxygens. And so I end up getting 122.55 grams per mole for that. So I'm going to put my conversion factor down. I'm dividing by the molar mass because I want to cancel out grams here. And remember, it has to go diagonal, so it has to go on the bottom. And now I've converted to moles of potassium chlorate. I then want to convert to moles of oxygen, so I use these coefficients in front of the potassium chlorate and the oxygen. I know that I want to cancel out moles of potassium chlorate, so that's going to go on the bottom here, and I am converting to moles of oxygen, so that goes on the top. So my moles of potassium chlorate cancels out, and I'm left with moles of oxygen. And so I get that 10.5 grams of potassium chlorate is going to produce 0.1285 moles of oxygen. So this is my N in my ideal gas law. Okay, so I now have that last given right here, which I then can use in my equation in order to find the volume that's produced. So we get volume is equal to my N, which is 0.1285 moles of oxygen gas. R is, which is the universal gas constant, times my temperature, which is 298 Kelvin, divided by our pressure, which is 1 atmosphere. And I end up getting that the volume of oxygen gas produced is 3.14 liters. So again, you've done this before, right? We know the ideal gas law. We know how to do stoichiometry. So now all we're doing here is we're putting those things together. So usually what you're going to be doing is you're going to be using stoichiometry in order to find number of moles, N, in your ideal gas law. Or maybe you're doing it the other way, but that's how you're going to be doing those two things that you already know how to do. All right, second example here. I have this beautiful chemical reaction, and I want to know what volume of gas at standard temperature and pressure will be produced if 3.7 grams of C2H2 is burned. So I have 3.7 grams of this, and I want to know what volume of gas will be produced. All right, notice that I just say gas. I don't say volume of water gas, of steam, or volume of carbon dioxide gas, or something like that. So like I said, just like the previous problem, we need to find N first. from stoichiometry in order to plug it into our ideal gas law to find volume. Now, like I was just saying, the other special thing about this is that I just ask for gas. So notice how both of our products are gas here. So we're going to have a conversion factor that looks like this. 2 moles of C2H2 produces 6 moles of gas. Now you might be thinking, where is she getting 6 moles of gas? Well, both my H2O and my CO2, those are both gas. See these little subscripts here? So because they're both gas, I want the total moles of gas. So 2 plus 4 is 6 moles of gas total. So this is going to be my last conversion factor to find the number of moles of gas. So I'm going to start with my given, which is 3.7 grams of C2H2. I'm going to convert to moles of that because I know that in order to convert from one thing in a chemical reaction to another thing in a chemical reaction, I need to first convert to moles. Carbon has a molar mass of about 12 grams per mole, and then hydrogen has a molar mass of 1. So we get 12 times 2, which is 24, plus 2, which is 26. So I'm going to divide this number by 26 grams of C2H2 per 1 mole of C2H2. So grams is going to cancel out. And then I'm going to use my conversion factor that I showed you on the last slide in order to convert to moles of gas. So I know that 2 moles of this C2H2 is going to produce 6 moles total of gas. So that's going to be 0.427 moles of gas produced. Now what I'm going to do is I'm just going to use my ideal gas law in order to solve for the total volume of gas produced. Again, I just divided both sides of this by pressure in order to solve for volume here. If you want to just plug pressure in here, that's totally fine as well. So we end up getting the volume produced is equal to our number of moles, which is 0.427 moles, times my universal gas constant R, 0.0821, times my temperature, which this is standard temperature, which is 273 Kelvin, divided by standard pressure, which is 1 atmosphere. So we end up getting 9.57 liters for our volume produced. All right. So this is example number 2. Now I want to show you one other way to do this, and it's very special because we can only do this way at standard temperature and pressure. All right, that's what the title says. I want to move myself back though. Okay, we can only do this at standard temperature and pressure. So if we're not at standard temperature and pressure, then you cannot use this way when you do gas stoichiometry. All right. Now, the reason that we can only use this way at standard temperature and pressure is because at standard temperature and pressure, if I solve for the volume of 1 mole of gas, again, R is always constant, standard temperature is 273, standard pressure is 1 atmosphere, I get that 1 mole of gas is equal to 22.4 liters. So because I know this, I can use this as a conversion factor. 1 mole of gas equals 22.4 liters. But again, this is at standard temperature and pressure only. So you cannot use this always. You can only use it at STP. Since my example number 2 is at STP though, I can use this conversion factor. So again, if we just start with our given quantity, which was 3.7 grams C2H2, I'm then going to convert to moles of C2H2 using my conversion factor, molar mass on the bottom. So grams cancels out. I then have moles of C2H2. I then use my conversion factor with those coefficients. So 2 moles of C2H2 produces 6 moles of gas, just like I did before. But now that I have moles of gas, I can use my new conversion factor. So 1 mole of gas will go on the denominator here because I want to cancel out moles of gas and convert to liters. So 1 mole of gas goes on the denominator, 22.4 liters goes on top, and moles of gas cancels out, and I'm left with my unit of liters, which is what I want. And so I get 9.56 liters here, which is very, very close to the answer that I got on the previous slide, 9.57. So again, you can do it this way, but it has to be at STP. So it has to have a temperature of 273 Kelvin and a pressure of 1 atmosphere in order to use this conversion for stoichiometry. All right, so those are my 2 examples for gas stoichiometry. Let me know if you have any questions on this stuff, and good luck on your checkpoint.